Okay, so to remind, I did a format modification of homework task 4. So just remember, homework task 4 is already been posted in Blackboard. I sent you guys a message. Homework task 4 is basically 5 problems. Well, 5 problems, but for 2 of the problems, you have to do the other things. It's this one, problem number 5, exercise number 6, and 3 exercises from this section. Okay, and we're going to do some more exercises today, so you have more examples. Now, this homework task is individual. And the idea is for you to turn this in by next Friday. I was kind of evaluating, because originally I said that for you guys to turn it in on Monday coming back. But really, and just trust me, it's better for you to do it this Friday.
I'm going to be doing it on Sunday like that.
You're giving us
Exactly. And so, at least in my class, you're not going to have necessarily anything to do on the break week. And when we come back, you'll have the solutions and you'll be ready for the exam. And it's not that much, the problems aren't that long or difficult. So what we're going to do today, we already did problem number 2. We already did problem number 2. Now let's do problem number 4. Okay. And remember that the topic that we're talking about right now has to do with energy in a capacitor. So we're looking at energy in a capacitor, and we're trying to link things up with also with other things we've seen. So it's a similar connection. So suppose I have a 9-volt battery, okay, and I've got 2 capacitors, a 2 microfarad capacitor and a 7.4 microfarad capacitor. And I'm being asked to find the charge and energy stored in each of the capacitors for 2 situations. First, if they're connected in series to the battery, and another if they're connected in parallel. Okay, so let's see how we can approach that. And by the way, I'm going to ask for your help, support with regards to calculation. So remember, you've been very good with regards to that in the classes. So yes, your calculations that we can verify. Okay, so I'm going to switch over to the whiteboard and. We're doing number 4. If you want to take a screenshot, go ahead. Okay, so sure, go ahead. Okay, I'm gonna jump over here to the whiteboard. There we go. Okay. So this is problem number 4. And remember that we're going to be doing it. There's 2 parts of problem number 4. It's part A and part B. So right now we're going to be doing part A. Okay. So it's problem number 4. And we are doing A, and the A situation is in series. And so what we have is that we have the following circuit. We've got a circuit where we've got a battery. There's many ways we can represent a battery or a power supply. Right now, I'm going to be using, at least for this unit, this nomenclature. So a battery or a power supply in a circuit, we can just represent it with a circle and a plus and a minus. It's a DC power supply. Right now, for these analyses, we don't care about the polarity. I'm just signaling it there because the battery should have some sort of reference of polarity. So that's the way we represent the battery. For those of you who took a screenshot, what is the value of that battery? 9 volts. So it's a 9-volt battery. This could be one of the square batteries that have 9 volts. And then it says that we have 2 capacitors, and these 2 capacitors are connected in series. So I'm going to draw 2 capacitors. that are connected in series with the battery, okay? What is the value for capacitor 1? I'm going to call this one over here on top capacitor 1. 2 microfarads. I'm going to call this one capacitor 1. It's 2 microfarads. And capacitor 2? 7.4 microfarads. And what am I being asked to find? I'm being asked to find, in the end, I want to find the charge in each of the capacitors. And I also want to find the energy that's stored in each of the capacitors. Now, up to this point, we have talked about charges, energies, etc. With a situation like the defibrillator, with a situation where we only have one capacitor. But now we've got more than one capacitor, and if we have more than one element, they're going to be connected somewhere, either in series or in parallel. In this case, it's going to be in series. So I'm going to walk through the procedure that I'm going to do here is similar to something I'm asking you to do in the second part of the homework section. We're going to do another example as well, where basically I have an array of capacitors, and I need to find values for either charge, voltage, energy, or whatever in the individual capacitors. So there's a kind of I'm going to try to do a kind of like a systematic procedure to do this, okay? And I similar to the ones we've done, and I urge you, or I suggest you to follow this sort of systematic procedure when you're doing these circuits. Because, by the way, in next learning module, we're going to be working with similar things, but instead of being capacitors, there's going to be another symbol, which is called a resistor. And then in the fourth learning module, we're also going to be addressing it, but instead of it being a resistor or a capacitor, it's going to be an inductor. So kind of the procedure we're going to be following, it's very similar. Go ahead. Jessica.
So what is the circle?
The circle, right now, there's many ways to represent a power supply or a battery. Right now, I'm using this symbol, which is basically to represent a battery. I'm going to use a circle and a plus and a minus. You might find different symbologies for that, but right now I'm going to be using the circle one because it's simple. Okay, so I'm gonna be going through the procedure step by step. Stop me if you have any questions. So, whoa, I got a little bit dizzy there. Give me a moment. Let me drink some water. Maybe walked too quickly from my office over here. So first off, we know because of the problem says so that the connections are in series. So this connection of capacitors right here is a series connection, okay? Now, the first thing I'm going to do is that I'm going to find the equivalent capacitance. That's the first thing. But remember the other exercises where we had a bunch of capacitors and I told you, find the total capacitance. That's the first thing we're going to do. And for that, we're going to forget a little bit about the power supply. We're just going to be focusing on the capacitance. Okay. So there is going to be a new circuit. I'm going to redraw it over here. That is going to be this total capacitance that we have here. Oh, excuse me, Andrea? There's going to be a new capacitor here that I'm going to call capacitor 1, 2, which is actually the total capacitance of the circuit because that would be it. And capacitor 1, 2, we know how to calculate that capacitance, right? It's the reciprocal. So capacitor 1, 2, and I'm just going to write it down here. It's going to be 1 divided by capacitor 1 plus 1 divided by capacitor 2, everything to the -1. And I'm going to trust you guys with calculation. So I'm just going to write it down here. It's going to be 1 divided 1. Oh, that's worse. Okay, give me just one moment here to write this down, and then you can give me the result, Viviana, so we can corroborate. 1 times 10 to the -6 Plus 1 divided by, what is it, 7.4 times 10 to the minus 6. And so capacitor 1, 2, which is actually the total capacitance, would be, what value did you guys get?
1.576 times 10 to the minus 6.
So rounded out, it would be 1.57 times 10 to the minus 6. And this is going to be the total capacitance of the circuit. Why? Because that's the most simplest reduction that we can do. Okay. Remember, if you have any questions, ask. I'm going to pause here so you can write. So right now what we found is the total capacitance. Go ahead. Yes, sir.
I don't know where to put the. Oh,
Remember, we mentioned this when we're doing the operations. Remember that the order of the operations in your calculator, it should be 1 divided by this, then 1 divided by this, add them up. And then the result is to the minus 1. And I forgot to write to the minus 1 up here. Okay. Okay. And so what does this mean? It means that we've got the defibrillator. We have the defibrillator. And in the previous defibrillator, we had only 1 capacitor. Right now, the defibrillator has 2. But if I would want to substitute these 2, and instead of having 2, just have 1, I could put this capacitor. So remember that total capacitance is the equivalent capacitor of many capacitors. It's going to be equivalent. I could substitute for that. Okay. Okay. Now, the next thing we're going to do is the following. I'm just going to tag it here. These 9 volts is the total voltage of the circuit. So I'm going to call this, these 9 volts, I'm going to call it the total voltage of the circuit. Okay. And so, let's see if you guys remember and start lifting up. If I have a capacitor in the circuit, there's 3 things I can have in the capacitor, or 3 things I can know. The capacitance, the charge, and the voltage. So right now I have the total voltage, I have the total capacitance, I can find the total charge that's being stored. Is that clear? And how do we do that? Well, we use I'm going to write it down up here. We have an expression. I'm going to write it down in pink. I'm going to write it down over here as a note in pink. Q equals C times V. Okay. Q equals C times V. So that's the expression we're going to be using. So we have the voltage and the capacitance. We can find the total charge of the circuit. Yes.
We use the one of U equals C times V squared over 2 to find the energy.
Yes, but we're not there. We're not there yet. We're not. Yeah, we're not. The answer to your question, Andres, yes. If I were to say find the total energy stored in the circuit, yes, you have that expression. You have the capacitance, the total capacitance, total voltage. You can find the total energy. That is correct. But right now we're not finding the total energy. Right now we're in the charge, and we'll get to that in a moment. So the total charge is going to be equal to the total capacitance times the total voltage. So the total charge is going to be, the total capacitance is 1.57 times 10 to the minus 6 farads. And the total voltage is 9 volts. So what is the total charge we have in this circuit?
About 1.42 times 10 to the power of negative 5.
1.42 times 10 to the negative 5, and these are coulombs. We have to be a little bit careful to not get confused because we're using the C to represent capacitance. And remember that the units of charge are volts. Okay. Questions with the total charge?
No.
And now let's go to what Andrea was saying. So another variable that we're interested in is the energy. So the potential energy, correct, potential electrical energy. So let's say that we wanted to know the total energy that we have in that circuit. We've got the three things we need: voltage, charge, and capacitance. And there's a few formulas that we could use. I'm going to write them down here. Where can I write them down? I'm going to write them down here. Remember. So help me out here, because so the three versions of the formula: U is equal to 1/2 CV squared. That's one of them. U is equal to 1/2 QV.
And then the 1/2 Q squared.
Yep, Q squared over C. We can use any of those expressions to find the total energy, and let's use the one that Andrea was mentioning, because before we had the charge, we already had the voltage and the capacitance. So U total, the total energy, is going to be equal to 1/2 CV squared, which is 1/2 of 1.57 times 10 to the minus 6 farads times 9 volts to the square. And that total energy that we have is equal to how much? How much? 6.36 times 10 to the minus 5. I was about to ask that. What are the units? Joules. Joules are the units for energy. Minus 5? Minus 5? Okay. There we go.
What do you say joules in Spanish?
Actually, it said joules. 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 It's like it's pronounced joules.
I noticed something.
What did you notice? I'm scared. Excuse me? You've never heard me speak Spanish? No, there have been students actually that have never heard me speak Spanish outside of class, outside of the semester.
I have. When we have donuts.
Can I see what?
I don't remember that, but I was.
What type of accent in Spanish would you like? Actually, not even Mexican. I mean, I'm talking about other countries. Just because I
No, Spanish accent.
Oh, Spanish accent. I don't have anything prepared. I'll give a brief summary of what we did. I don't want to do something new and because I'm going to get confused in my head. So, pues okay, pues muy buenas tardes. Vamos a hablar un poco acerca de la capacitancia y el voltaje en un circuito eléctrico. Lo que hemos hecho hasta ahora es que hemos calculado la capacitancia total del circuito con los 9 volts. Lo que ustedes han hecho, lo que habéis calculado es que habéis calculado la carga total y habéis calculado también la energía total del circuito. Y lo que seguiría ahora es que ahora vamos a desglosar el circuito para poder regresar y poder encontrar cada uno de los valores. Okay. Let me just say something. That is extremely, we have, my wife and I would say we're good parents, but we do some weird parenting sometimes where we don't recognize what we do. So I don't know if I mentioned this earlier, but I have a very good friend here at CETIS that's called Monica Lopez. She's from Spain. She's in charge of the MBA here at CETIS. I work with her. She's really great to work with, and we're good friends. And she's from Spain. So before she was going to go to Spain last semester, we invited her to our home so we could have dinner. And my daughter, who likes stuff about other countries, I'm like, oh, there's a friend of mine that's going to come over and she's from Spain. Okay. And remember that we talked about Spain, and I started doing that. I started doing what I was doing right now. And my daughter was, et cetera, et cetera. And then you're going to be good when Monica comes, right? You're going to be good. And she started doing that. And she, cuando llegue Monica, voy a empezar a hablar. And I'm like, no, do not do that. I was joking. Please do not do that. That's going to be really, really embarrassing. That's going to be really, really embarrassing. But please do not do that. And as a preemptive thing, I called Monica and I told her, you know what? When you come over, my daughter might, because in her head, it's like if es que si no lo hago, papi, no me va a entender. And she was literally thinking in her brain that if she didn't speak Spanish of Spain, my friend would not be able to understand her. I mean, she wasn't doing it in a bad way. And I told Monica, you know what? Oh, if you come over, my daughter might do that. Please don't be offended. She's like, oh no, don't worry. She brought her a drag, and we had a wonderful time. We had a wonderful time. Fast forward, on Monday, I believe, I needed to send Monica a voice message, and I had just picked up Sarah. And actually, I think I've got the voice message here. It'll be easier to show you instead of explaining. Yeah, here we go. Oh no. Yeah. What happened in the voice message was that I was telling Monica a few things. Oh, this and that. I sent you some documents, etc. Oh, and by the way, somebody wants to say hello to you. And I put the phone on like this for Sarah, and she's like, "Hola, ¿cómo estás?" Ah, no. Oye, ¿cómo estás? And I'm like, I'm not gonna erase the message. No, I mean, she's just being that way. So children absorb a lot of things, and we do a lot of accents and a lot of voices and stuff. And so people who know me know I do voices. So yeah, but you haven't heard me speak normal Spanish. You just heard me speak Spain.
No, once I just talk Spanish and it feels weird. Like when you hear like people speak English, speak another language, it feels the same way.
I remember when in the engineering conference,
Symposium or something like that?
It was like a symposium.
you appeared, I was there.
I gave a workshop or something, I think, or I don't remember something. Oh, there was a panel. Yeah, there was a panel, and I was speaking with some people abroad.
Yeah, that one.
No, yeah, I kind of find it funny to do. My wife thinks it's extremely annoying, but I find it fun. So that's that. That was that. I'll do different voices in other classes. I can and some impersonations, but let's not do all of them this class, or else there won't be any expectation. So what we've done up to this point, we found the total charge, total voltage of the equivalent circuit. Now, for these sorts of exercises, and actually for the ones of part 2 for homework task 4, what we need to do is once we get to this point, we need to sort of unravel things and go backwards to find the individual voltages, charges, energies, whatever of the original circuit. So this process that I'm showing you, so first we've got the original circuit like the exercises we did before. We identify the series in parallels and boom, 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 we find the total capacitance. From the total capacitance, we find the total rest of the things, voltage and charge. And now we're going to go back, okay? And to go back and do the rest of the things, I'm going to put another remember box here. This is new. I just came up with the remember boxes. This is gonna be useful, I think, to do the remember pink boxes and the problems. And let's see if you guys remember. In series, what is the same and what is different? There was a slide actually in the PowerPoint, series and parallel. Some things are the same in series and some things are different. What is common? Right, well, that's actually the correct way. The what? The charge is the same. So Q is the same. And what is different then?
The voltage.
Oh,
Voltage is distributed.
What about the energy?
We're going to get to the energy in a moment. We're going to get to the energy in a moment. That's the energy applies to everything, and that's something we're going to talk about in a moment. And in parallel, the opposite occurred, right? The voltage is the same, and the charge is distributed. Okay, so let's remember those principles. So now I'm going to go back. I'm going to return to the original. I'm going to return to the original circuit. I'm going to now go from here to here. So this is the question I'm going to ask. Capacitor 1, 2 is the total capacitance. Okay. By the way, something that I can say as well is that QT is equal to Q12. And UT is equal to U12. We're not going to talk about, we're going to talk about the energy at the end. Okay, so right now let's focus on charges and voltage. So the question here is the following. Capacitor 1, 2 comes from a series or a parallel array?
Series.
A series. So if I go now from here to here, what is common? What is the same in series?
Charge.
The charge. So if I'm looking for Q1 and I'm looking for Q2, the charge in Q1,
Will be the same as Q2.
exactly, the charge in Q1, because they're in series, is going to be the charge in Q2, right? And that is going to be equal to the charge in Q12. Okay? Because they're in series. Okay? And what is that value? We just have that value there. It's 1.42. So the charge of Q1 is going to be 1.42 times 10 to the minus, what is 5 or 6? 5 coulombs. And the charge in Q2 is also going to be 1.42 times 10 to the minus 5 coulombs. What is going to be different? The voltage. So voltage 1, and we'll go to the energy in a moment. I just want to do the voltages as well because this is how you're going to be doing the problems from the homework test. Voltage, how can I calculate voltage 1? Well, I can use the Q equals CV formula. Voltage 1 is going to be equal to Q1 divided by capacitor 1. Q1 is 1.42 times 10 to the minus 5. And capacitor 1 is 2 times 10 to the minus 6. What is this value calculated? And voltage 2.
we can use that formula to calculate just one voltage and the total.
Yes, it's the same expression. That formula is the formula for the voltage in a capacitor. So it can either be the total one or an individual. It's the same expression. And this would be 1.42 times 10 to the minus 5 coulombs divided by 7.4 times 10 to the minus 6. So what would those two voltages be if you could do those calculations?
P1, I got 7.1.
7.1 volts, correct? And mentally, I can calculate that voltage 2 should be 1.9.
Yes.
Now, can somebody tell me why is that? Why could I mentally calculate for this situation? Because the voltage is distributed. There you go, Dio. The voltage is distributed. Remember that this has to do, we're gonna link it up with energy. Remember that energy isn't created or destroyed, it's just transformed. So if I have a 9-volt power supply, and that is giving voltage to these two capacitors that are in series, it has to be distributed somehow. And so if one is 7.1 and one is 1.9, and one is 7.1, the other is 1.9, the total should be the 9 volts. So if I add these two, I should get the 9 volts, which is the total voltage. Okay. Now that we have everything, we can find the energy. So the energy in capacitor 1, we can use actually, we can use any of these expressions to find the energy, because right now we have everything. So we can use any of these three expressions to find the energy. I'm going to use the first one. You can use any one, you should get to the same result. It's going to be 1/2 of C1 V1 squared. This is going to be equal to 1/2 of the capacitance 1, which is 2 times 10 to the minus 6 times voltage 1, which is 7.1 volts elevated to the square. And U1 is going to give us a certain value. And then U2 is going to be equal to 1/2 of C2. Oh, yeah, we're calculating, what we calculated originally is the total one, now we're calculating the individual. 1/2 of C2 V2 squared equals 1/2 of 7.4 times 10 to the minus 6 coulombs times 1.9 squared. And U2 would be equal to, we'll calculate both of them, please.
The first one I got 5.04 times 10 to the minus 5.
5.04 times 10 to the minus 5. These would be joules. And please calculate U2.
Well, it would be 1.
It should be. It should be.
I know, 32.
Yep. 1.32, 33.
Times 10.
Now,
Times 10 to the minus
apart. So the observation, the we're making, we have a total energy, which is 6.36. Energy as well as voltage also has to be distributed. So if we have a total energy of 6.36, that energy is also having to be distributed within the element. So if I take the energy of 1 and 2 and I were to add them,
Needs to be 636.
this is going to be equal to the total energy. Okay, so now what we're gonna be doing for situation A, the capacitors were infused, now they're gonna be in parallel. And let's see what changes when they're in parallel. So we're gonna do the similar procedure. This is problem 4, part B. So now we're gonna have the same 9-volt battery. But now the capacitors are going to be connected in parallel. It's the same two values of capacitance. So this is going to be C1, which is going to be 2 microfarads. This is going to be C2, which was 7.4 microfarads. And now the difference is that now they're in parallel. So these, or this connection here, is a parallel connection. This is going to give us a equivalent circuit where we've still got the 9-volt battery. And there's going to be an equivalent or total capacitance here that I'm going to call C12. Now that equivalent or total, oh, and the things we're looking for the same things. We want to know the charge in Q1. I'm sorry, the charge in 1, the charge in 2, the energy in 1, and the energy in 2. And so if the capacitor or this C12, if this capacitor comes out of a parallel connection, we can calculate the total capacitance. And so the total capacitance, or the capacitor 1, 2, is going to actually be the sum because they are in parallel. So this is going to be 2 times 10 to the minus 6 farads plus 7.4 times 10 to the minus 6 farads. This is going to be 9.4 times 10 to the minus 6 farads. And this is going to be the total capacitance. Now, similar to what we did previously, we have the total capacitance. Now let's find the rest of the things. We know that the total voltage is 9 volts. And we can find the total charge. The total charge is going to be capacitor 1, 2, I'm sorry. The total capacitance times the total voltage, this total charge is going to be equal to 9.4 times 10 to the minus 6 farads times 9 volts. And how much would that be? Please calculate that.
I got 8.46 and sent to the.
Colds. This is Q 1, 2, which is also the total charge. Okay. We can also find the total energy. We can use any formula we want. So the total energy would be, I'm going to use 1/2 of C total V total squared. This would be 1/2 of 9.4 times 10 to the minus 6 farads times 9 volts to the square. What would be the total energy?
Getting sent to the minus.
3.8 times 10 to the minus 4. And these would be joules. Okay. So now we've got the total, all of the elements, the total voltage, the total capacitance, the total charge, and the total energy. So first off, and I'm not going to write the remembers again, but see, now we're going to go back. Now we're going to go from here to here. In the case C12 is coming out of a parallel connection. What is the same in a parallel connection and what is different? The voltage is going to be the same. So the voltage in 1 is going to be equal to the voltage in 2, and that's going to be equal to voltage 1, 2, which is equal to the total voltage, which is 9 volts. And we talked about that actually, that if I have a battery or any sort of power supply and I connect anything in parallel to a battery, the voltage in the battery is going to be exactly the voltage in the elements is going to be exactly the same as the voltage in the battery. What is going to be different? The charges. So Q1 is going to be equal to C1 times V1. This is going to be 2 times 10 to the minus 6 farads multiplied by 9 volts. This is going to be equal to something there. And charge 2 is going to be C2 times voltage 2. 7.4 times 10 to the minus 6 farads. Multiplied by 9 volts. We've got these two. You could please calculate those. Actually, we've got enough space here. So
Now 1.8 to 10 to
okay, so for Q1,
Yeah.
Q1 is 1
Uh-huh.
1.8 times 10 to the minus 5 coulombs. And then Q2 is C2 V2. 7.4 times 10 to the minus 6 farads times 9 volts. Q2 is going to be please calculate Q2. 6.66 times 10 to the minus 5 coulombs. And what we should be seeing here is that if I grab these two and add them, it should be equivalent to the total capacitance. The total charge, I'm sorry. You're right, charge.
The
charge.
C is gonna be the-
Mhm, Yep, yep. Yeah, because of the columns. Yeah. Total, to the total charge. And lastly, we can calculate each of the energies. So the energy in one is going to be 1/2 of C1 V1 squared. It's 1/2 of 2 times 10 to the minus 6 farads times the U is we've calculated the total energy. Now we're calculating the individual ones. And then U2 is going to be 1/2 of C1, C2 V2 squared. It's going to be 1/2 7.4 times 10 to the minus 6 farads times 9 volts squared. Okay, so give me those two values. You don't necessarily have to calculate the totals. I'm just for these two examples that were being recorded, I'm doing all of the calculations you might need or be asked to calculate. So we really don't need the total energy to calculate the rest of the stuff. The only thing I'm trying to demonstrate in these two examples is that the individual energies are always going to be equal to the total. So we really don't need this value. They're not asking us for this. But they could ask us for the total energy. Okay, so what values did you get for U1, energy 1 and energy 2?
I calculated energy 2 first because I'm like that.
Okay.
I got 3 times 10 to the negative 4.
3 times 10. Joules, and so the other one should be 0.8. Mhm.
I rounded it up because it was technically 2.99.
Okay. And so again, if we were to add these two up, the result is the total energy. So, question for this one, before I make some comments about how well these calculations of energy and all that.
One question.
Right.
From the battery, does the energy flow, or does the current flow from the positive to negative or to negative to positive?
That's a good question. In the case of, right now, we're still kind of in the electrostatics part because the capacitors are being charged, but really the charges aren't being moved. In the next unit, we're going to formally define the next sewing module, which is electrical circuits. We're going to formally define what it means for current to move and how it moves. And so the movement of electrons, which is called current, we have a reference for that. So usually the reference we're gonna take is that we're flowing from positive to negative. I'm just saying that that's a reference because you could put it the other way around in the circuits we're gonna see next unit, and you're still gonna get congruent calculation. It's just a way to establish a certain reference for circuit analysis. So usually we are going to be saying that it's going to be flowing from positive to negative, if it's a DC.
But technically it doesn't, for our calculations, it doesn't matter which way it goes.
It doesn't matter as long as you establish the same convention of analysis for all of the circuit. So you can't say, oh, for this part of the circuit, it's going to go in one direction and for the other. You have to establish it. Questions with these calculations before we? No. Now, let me just take a pause here in this example because we're doing calculations and all that, but I'm gonna see if I can design an exercise. Let's see if I can design an exercise based on your electrical bill. That would be really interesting. That would be really fun.
Oh, when the Mexicali prices,
Yeah.
it would be.
No, the electrical bill, like you have in your, if you notice, because we're talking about joules. So, we're talking about joules, and that could be as well related to, because we're talking about energy and we're gonna be talking about power. And so, in the end, we've got a 9-volt power supply, and each of these elements, the power supply is providing a certain amount of energy, and that energy is being distributed into each of the elements, right? So imagine that each of these elements is a device in your house, right? And each of the elements requires a certain amount of energy to be able to work. So right now, for this example, the power supply is fixed. I can't give more than 9 volts, but imagine that the power supply is variable, right? And each of these elements requires a certain amount of energy to work. If I were to ask you, let's say that instead of capacitor 1 is your washing machine, and capacitor 2 is your microwave oven. Well, right now, that's a good question that Vivian is asking. Right now, don't worry how we're connecting it. I want to talk a little bit about energy. And actually, energy doesn't necessarily depend, the calculation of energy doesn't necessarily depend on the types of connection. So I want to talk about a little bit about energy. Imagine that we've got what did I say? The washing machine, did I say? And the microwave oven. Of those two devices, which device is consuming more energy?
What the machine that washes.
Is it?
Yes.
The first one was the washing machine. How many joules do we have in the washing machine?
In that circuit.
For this situation, obviously depending on how we connect it is going to change, but for this situation, which one is consuming more energy? The second one, because it's got more, it's asking for more energy. It's 3 joules. So should a microwave oven consume more energy than a washing machine?
No.
All of the devices that are in your house are consuming energy, and they're draining that energy from the electrical grid. And so that's why it's important to have efficient devices in your households. Because if I have a lot of devices and a lot of devices are consuming a lot of energy, then that's the value of the power supply that I need for to be able to make those devices work. And so I don't know if you notice in your electrical bills, if you've seen them, that there are ranges. So let's say if you consume up to a certain amount of they're called kilowatt hours. If you consume a certain amount, then each of the kilowatt hours is going to cost a certain amount. But if you go beyond that, then it starts getting higher. Okay?
But how do they
The measure, there's many ways to measure energy, so they measure it in what's called kilowatt hours. And so depending on the range that you have is the rate you have. And so if you have a lot of devices that aren't efficient, then even if you use them a little, you're gonna be consuming a lot of energy. And so let me see if I can design an exercise so we can analyze our electrical bill. That'd be really interesting with regards to these terms or concepts. The idea is for us to consume the least amount of energy from the power supply, which in this case would be the grid. Okay. Questions with this one? With this? Let me take a screenshot. No, we're gonna break here for now because we're not gonna be able to finish the next one.